Welcome back to The Explainer. Today we're jumping right into the fundamental language of how the universe moves. Whether it's a car racing down a straightway, a planet orbiting a star, or just an apple falling out of a tree, there's a strict set of rules governing all of it. This is the realm of kinematics. In this explainer, we're going to break down the core concepts of one-dimensional motion. We'll build this up from scratch, starting with where we are, moving to how fast we're going, and ending with how we accelerate. It's an awesome ride, so let's get into it.
Let's kick things off with a bit of a historical mystery involving Galileo and the Leaning Tower of Pisa. Now, for centuries, people just naturally assumed that heavier objects hit the ground faster than lighter ones. I mean, it makes intuitive sense based on our everyday experience with air resistance, right? But Galileo completely upended that assumption with his legendary experiment, dropping objects of different masses right off the top of the tower.
Which brings us to this wild, entirely counterintuitive question. Why do a feather and an apple fall at the exact same time in a vacuum? The free fall of these objects in a vacuum is actually a perfect textbook example of one-dimensional motion under gravity. The crazy result of Galileo's findings is that the time of the fall has absolutely nothing to do with the mass of the object. But to truly understand the mechanics of why that happens and how we even measure it, we first have to lock down the basic vocabulary of motion.
So, here's how we're breaking it down today. 1. Frames of reference. 2. Distance versus displacement. 3. Speed and velocity. 4. The mechanics of acceleration. And finally, reading motion graphs.
Section 1. Frames of reference. Where in the universe are we? Before we even try to measure movement, we have to establish our starting point, because believe it or not, position is entirely relative to the observer. If a body doesn't change its position over time relative to a specific frame of reference, well, it's at rest. If it does change position, it's in motion. But to define that position, you always need two things: a distance from an observer and a direction with respect to that observer. That's exactly why position is characterized by a vector.
Think about this classic analogy from our source material, the train and the tree. Imagine you're standing still on a train platform. You look at a nearby tree and obviously it's at rest. Now imagine someone else who's sitting in a high-speed train zooming past that exact same station. To them, looking out the window, that tree appears to be flying backward. It's in motion. The brilliant part? Both of you are completely right. The observations are different simply because the first person is using a reference frame at rest and the second is using one in motion. Rest and motion are purely relative.
Section 2. Distance versus displacement. How much do we actually move?
So we know where we are, but what happens when we move? Physics gets very specific here, and the crucial thing is distinguishing between the actual path you walked and your net change in position. Distance is the actual physical path length you covered. We call that a scalar quantity. It's just a magnitude, no direction. It can never be negative and it never shrinks as time goes on. Displacement, though, that's a vector. It's the shortest straight line connecting your start to your finish. Because it's a vector, direction absolutely matters. If you walk a giant circle and end up right where you started, your distance is huge, but mathematically, your displacement is a big fat zero.
Just picture a particle moving from point A up to point B and then down to point C. The actual distance traveled is the length of path AB plus the length of BC. But the displacement, that's just a straight, direct arrow cutting right from A to C. This perfectly illustrates why distance is always greater than or equal to displacement. Distance never decreases, but displacement sure can, especially if you start turning back toward the starting line.
Section 3. Speed and velocity. How fast are we going? Once we know exactly how far we've gone, the next logical question is, how fast did we do it? And just like distance and displacement, we've got two different concepts here. Speed cares about the actual journey. It's the rate of distance covered over time, a scalar quantity. Velocity only cares about the destination and the time it took. It's the rate of displacement over time. It's a vector, meaning if you change your direction, even if your speedometer stays exactly the same, your velocity is changing.
I absolutely love this scenario because it highlights the hilarious reality of vector math. Picture a guy walking from his house to a market 2.5 kilometers away. He takes his time, strolling at 5 kilometers per hour. But he gets there and the market is closed. Annoyed, he immediately spins around and power walks back home at 7.5 kilometers per hour. We can calculate his average speed over that 40-minute window, and it comes out to roughly 5.6 kilometers per hour. But physically, his net displacement is 0. He is right back on his couch. So despite all that sweating, his average velocity for the entire trip is a flat 0.
Section 4.
The mechanics of acceleration, changing your speed or your direction.
This leads us right into the concept of change. If velocity is how fast your position changes, acceleration is how fast your velocity changes. Acceleration is also a vector, and because velocity includes both speed and direction, a change in either of those means you're accelerating. You can accelerate by just changing your speed in a straight line, like an apple dropping from a tree. You can accelerate by just changing your direction, meaning you are literally accelerating even if your speedometer doesn't move, just by turning your steering wheel. Or you can change both at the exact same time, which gives us projectile motion.
Think about a projectile flying through the air. The acceleration from gravity is a constant vector pointing straight down the entire time. As the object flies, that downward acceleration constantly acts on the velocity at different angles. It literally bends the path into that familiar parabolic curve, changing both the speed and the direction simultaneously.
Section 5. Reading motion graphs. Visualizing the data of movement.
Let's put some numbers to this and translate the math into a visual story. We'll track a particle's position along an x-axis over 3 seconds. At 0 seconds, it's at -2 meters. At 1 second, it's at 0. At 2 seconds, it's at 6. And at 3 seconds, it's out at 16. Just look at the jumps in position. They're getting larger every single second. First it moves 2 meters, then 6 meters, then 10 meters. This increasing distance covered per second, that is the literal mathematical signature of acceleration.
When you map this kind of data out on a position-time graph, the steepness or the slope of the line tells you the instantaneous velocity. If the line is totally flat, the slope is 0, meaning you're at rest. If the line is straight but angled upward, your velocity is constant. But a curving line? That means the slope is increasing. The velocity is changing. And as we just established, a changing velocity means you have acceleration.
We've covered a ton of ground today, from Galileo dropping weights to the strict mathematical rules separating scalars and vectors, right up to visualizing acceleration. But I want to leave you with this slightly philosophical physics thought to ponder. If you were born in a local hospital, you travel the whole world, live an incredibly adventurous life covering thousands and thousands of miles, but eventually, many decades later, you pass away in that exact same hospital. Your life's net displacement is 0, which means the ultimate average velocity of your entire life is exactly 0. Something fun to think about next time you go for a run. Thanks for hanging out with me on The Explainer, and keep learning.